Okay guys, so welcome back again to another video about inorganic chemistry. So in this video we're going to talk about the reactions of organometallic complexes, right? So basically there are main 5 reactions which I'm going to talk about with you. First thing is the oxidative addition reactions, and then we have reductive elimination, migratory insertion reactions, and beta hydride elimination, and also the dissociation and association reactions, right? So I'm going to do 5 videos about each of these reaction types. So we will move on to the first type of reactions, which is oxidative addition reaction. So I will explain this by a simple example. First of all, you need to know is that there are few mechanisms which this reaction can undergo, right? So I will go with each of the examples. We are going to talk about main 2 mechanisms. So I will explain it with the example. So first one, let's say we have a complex like this. We have iridium metal center, so ppH3, and we have another ppH3, and we have carbonide, and we have, let's take another carbonide. Okay, now I'm going to react it with hydrogen gas. Okay, so this is our reaction. So what happens now is we have our ppH3, here we have the ppH3, carbonyl. In the transition state, our metal center will start binding to our hydrogen molecule, right? This will start binding to our hydrogen molecule, and then what happens, this bond will be broken to form a complete bonds with our metal center. So here we have ppH3, and here we have hydrogen, and we have carbonyls and carbonide. So this is our first mechanism, which we call as concerted type mechanism. If you know the term concerted, if you have gone through the concerted this term before, you will know what it means, right? Concerted means simultaneously. So this is one step reaction, right? This is one step reaction because when this iridium, our metal center, binds to our hydrogen, simultaneously the hydrogen will break its own bonds with this, right? When this bond is forming, this bond will be broken. So this is called the concerted type mechanism. The bond breaking and forming will be happen simultaneously in the same time. Okay, now there are some few important details which we have to discuss about this concerted type mechanism. First thing is always the this addition product, right? This addition molecule, it has to be non-polar. The concerted type mechanisms, they favor the non-polar transition state. This is transition state, right? So first thing is this has a non-polar transition state, or in other words we can say this addition molecule, this adding molecule, this has to be non-polar. If the adding molecule is non-polar, you can mostly say the reaction will go on through concerted mechanism. That's the first thing. And the other thing is, right, always remember cis addition will be happen. What is the cis addition? Cis addition means, let me take another color. Okay, we will take red color. Cis addition means when the simultaneous bond forming and bond breaking happens and hydrogens is going to bond to our metal center, these are always at cis positions, right? I mean, you cannot see this hydrogen on this position or this hydrogen at this position. Like there will be no ligands in between these two hydrogens. Always these two added components, in this case we will talk it as hydrogens, these hydrogens are at cis position. That's why we call as always cis addition will happen. Okay, the next step, next point, Let me go back to another color. Okay. The next important topic is always the reaction is second order. Second order reaction. Why is that? You know simply like why is that, right? The rate is determined. Rate is based on our both two reactants, the hydrogen and our complex, both are taking place at our rate determined step, because this is only one step reaction, right? This is the transition state. So this is our basically reaction. This is our basic reaction. This is the transition state. So this is a one step reaction. That's why the both reactants are taking place, or both reactants are taking a part in our rate determining step, which makes our rate, it depends on the both hydrogen and our complex. So this is second order reaction. That's great. Okay, now let's talk about another thing. In this, this is not a very important thing, but you need to have a good idea about this. The kinetic isotope effect. Kinetic isotope effect. The kinetic isotope effect is not considerable, right? Not considered. Why is that? First of all, let me explain a little bit about the kinetic isotope effect. So, okay. I will take this in this the same thing. Okay. The kinetic isotope effect is, let's say I have replaced this one hydrogen with another deuterium. I have replaced one hydrogen with a deuterium, right? So now I have replaced this with deuterium. You know that based on these two isotopes, the mass will be different, right? Because of this mass difference, the reactions energy, such as the Gibbs free energy, enthalpy, these things will be different because the mass is different, so the bond strength are going to be different, like this. But the thing in this particular mechanism, the concerted type mechanisms or one step mechanism, is the isotope effect, kinetic isotope effects cannot be considered. Why? The bond breaking and bond forming are happening simultaneously, right? So let's say when you are forming the bond, due to the isotope effect is positive 7, right? The isotope effect on the bond forming is positive 7. Let's just say it, right? Just a simple example. But simultaneously a bond will be breaking over here, so same value will be negative. So when forming and breaking happening simultaneously, the isotope effect will be cancelled out. That's why we are telling in concerted type mechanism, kinetic isotope effect is not considered. I hope you got the idea about that. So this is all about the concerted type mechanism. So let's move on to the next mechanism, which is SN2 mechanism, right? Before we are going into the SN2 mechanism, I just forgot to mention one important thing. We calling this reaction as oxidative addition reaction. You need to have that idea about why we call it as oxidative addition reaction. It's basically about the oxidation state. If you calculate the oxidation state on iridium on here and here, you will see let's say this is at 0 state. When you calculate the oxidation state at this place, you will see it's +2. Always in oxidative addition reactions, right? In oxidative addition reactions, the oxidation state will be increased by 2 units. Yeah, by 2 units always. This is a common thing for oxidation addition reactions. Like, it doesn't matter what is the mechanism is, all the oxidative addition reactions have this character. So let's move into the SN2 mechanism. Okay, now in the next example, I will again explain it by a simple example. Let's take an example like this. The same thing, same iridium with carbonyl. Let's take another chlorine, and let's take a phosphine. Sorry, another phosphine. So now we are going to react this with CH3I. This is our molecule. So now what happens is, you can see the first what happens is our iridium metal center will attack our carbon on here, with it will cause to break up this bond. So we will have our product like here we have our CH3 over here. Let's take carbonyl over here, phosphine over here. The geometry can be different, right? I'm not interested in geometry. So here we have our complex, which is now positive charge, and our iodide will be in here too. In the next step, what happens? Next step, this iodide will come and attack to our iridium too. So now we have CH3, iodide, carbon monoxide, phosphine, chloride. So this is basically our final product. So this is a SN2 mechanism. So this mechanism follows the basic rules on SN2, like this is right. This is the same thing like SN2 mechanism. That if I tell specific things about this particular mechanism is, in the previous mechanism, if you remember, here we are talking about the non-polar, right? If you see a non-polar reactants with our complex, then it definitely most often go for the conservative mechanism. But in this case, we have a polar. This is polar group. So because of this polar group, this is go for the SN2 mechanism. You need to remember that, right? And this is again, this is second order reaction. This is a second order reaction with 2 steps, right? This contains 2 steps, but the rate determining step is the first step. This is fast. If I ask you why is this fast, right? Why is it fast? You must have an answer for it, right? Look at this. We have a positive charge complex and iodide. These are carbocation. These are anions and cations, right? Which are unstable, right? These are unstable cations. So they are going for the neutral compounds. So this is particularly stable compared to this is stable. So unstable to stable, which is has to be fast. Here look at this. This is stable, right? This is compared to other molecules. This is stable because it's neutral compound, but it's going towards a unstable anion and cation. So the rate determining step, or this step should be slow, like basic things, right? So these can be varied based on the solvent, right? You know the solvent effects, right? Solvent can change the stability of an anion and anion based on its properties. We will talk about it later. So this is a second order reaction. And other thing is, always remember trans addition will be happen. It's common for SN2 mechanism, right? Because now when the CH3 is connected to our iridium center, iodide is left over. So then the next step, iodide had to connect it to our metal center. Now it cannot come through this way, right? It cannot come to this way to form a cis bond. Why? There are so many repulsions, right? There are so many steric hindrances. Only path for iodine is through this way. So it's going to be trans addition reaction. Okay, and the same thing here, you can see our iridium has positive 1 oxidation state. In this case it has positive 3, which means the same rule for oxidative addition reaction, which is the oxidation state increased by 2. That is a very important thing, right? It's important not for the mechanism, for whole oxidative addition thing, right? If you see an oxidative addition, always remember your oxidation state will be increased by 2, and also your coordination number. Here at first you have 4 coordination number is 4, but now you have 6. Coordination number and oxidation state both will be increased by 2. Okay, now this is the basic thing about the SN2 mechanism. I hope you got the idea about it. There are some other mechanisms, right? Like radical mechanisms and also ionic mechanisms. So I'm not going to go much details about it. So maybe we will talk about it in our next videos. I will see about it. Like they are not that much important like SN2 mechanism and our concerted mechanism. These two are very important. You need to have a very good idea about it. Okay guys, so before we are going to wrap the session, there is a very important thing to talk about, which are the requirements for the oxidative addition. So basically these requirements, I'm going to talk about the perspective on metal center, like what condition do the metal center have as in order to undergo oxidative addition. First of all, if you look at the both these mechanism here, if you look at the both these mechanism, right, our metal center has to attack to other reactant, right? Our metal center has to attack the outside molecule. So the first requirement is there should be a higher electron density, right? There should be higher electron density on our metal center in order to go through oxidative addition, because our metal center acts as the nucleophile. It should go and attack to our other reactor. So the first condition is that, so higher electron density on metal center, or otherwise we can also tell you that lower oxidation state. If your metal center has like positive 4, positive 6, positive 5, like that kind of higher oxidation state, which means the electron density is much lower. It cannot act as a nucleophile in order to start the oxidative addition. So this is the first and important requirement for the metal center. And the next we have, okay, our metal center should be coordinatively unsaturated, right? I'm talking about the metal center, right? Metal center coordinatively unsaturated. What does it mean? Unsaturated, right? This means, like, look at here, our metal center is going to attack to our methyl group and gonna attach the methyl group to the metal center, right? What if your metal center already have another 2 coordination site? Like now there are no vacant site to add or vacant site to put our methyl group, right? There are already 6 coordination state, right? There are 6 ligands already, so there is no room to methyl to be attached or iodine to be attached. So there should be at least 2 vacant sites, because 2 ligands will be come to attach to our metal center. So there should be at least 2 vacant site in the metal center. That's why we are talking about, but that's why we are telling coordinately unsaturated metal center. Unsaturated means there should be vacant site, right? Metal center. Okay, the next requirement is our metal center should have, should have appropriate vacant orbitals, right? Should contain vacant orbital, because a bond is going to be happen, right? A bond is going to be formed. So in order to form a bond, there should be a vacant orbital. So basically it's referred to this one too, but there's a slight change. And then the oxidative addition ability increases, right? This increases along your periodic table, right? So if I take an example, right, let's take nickel, vanadium, platinum. The oxidative addition ability is increases to the downwards. Why is that? Because of the electron density, right? You know that platinum has a higher electron density than the nickel, because like with the increasing amount of electrons and energy states, platinum is acting more likely a nucleophile than nickel. That's why basically the nucleophilicity, right? The oxidation addition is based on mostly on nucleophilicity. You increase the nucleophilicity, you increase the oxidative addition ability. That's the basic idea about this. So these are the few points you need to remember, or you need to have an understanding about when you're talking about oxidative addition. So see you in next video.